Let's talk about the other two parts of this problem. Now that we've boiled down that big messy expression to just -4 times the cosine of 2t, we can take a look at the other questions. I happen to close my window, so the number 4 changed to a number 3, as you can see right here. But the question is still the same. Describe the maximum displacement with respect to the equilibrium position. And then the other part of the question is, how long does it take for the weight to first achieve its maximum displacement starting at t equals 0? So now that we've boiled down the functions to just -4 cosine of 2t, we have questions about things like maximum displacement and how long it takes to get there. So if we look at the graph of -4 cosine of 2t, we can see that there's kind of a limited scope of questions that I can ask you. I can ask you about the amplitude, I can ask you about the period, I can ask you about the horizontal shift, and I can ask you about the vertical shift. If I've got the function -4 cosine of 2t, the -4, there's no vertical shift, so the middle is at 0. The amplitude is at 4, so it goes up to a maximum of +4 and a minimum, down to a minimum of -4. Also, my period is going to be 2 pi divided by 2. My horizontal shift is 0, and it's negative cosine, so it starts at the bottom. So it's negative, and cosine starts at the bottom. The coefficient of 4 says that the amplitude is equal to 4. And the 2t said, the coefficient 2 says that the period is 2 pi divided by 2, or just pi. So we start here at 0, and we get to the bottom again at pi. So the question is, how far does it get from equilibrium? Equilibrium is our middle. And 4 is our max distance from equilibrium. And we want to know what that is and when that happens. Since our amplitude is 4, the maximum distance is 4, and the amplitude happens halfway through the period, which is pi over 2. Other variations of this question: how long does it take the spring to return to its original position, or then that's going to be the period, which is pi 3.14. But those are the questions that I can ask. Once we've boiled down our function to just -4 cosine of 2t, we just start asking graphing questions. Middle, amplitude, period, horizontal. Two questions. So what that means is that we could have just gone in here and graphed y equals 4 times the numerator of sine of 2t minus pi over 2. Oops. Plus 1, close the numerator, divide by the denominator of 1 minus 1 plus cosecant. I wrote minus down here. One plus cosecant of the same to 2x or t minus pi over 2. Notice that the graph that we're getting is just a negative cosine graph. Where here we're at the bottom, 0, -4. Oh, it's got a cosecant, so it's not defined. And here at the top, 4. And if we graph y equals -4 cosine of 2t, keep spelling 2 wrong, we get the same graph. The graphs are just right on top of each other. The only difference is that the original graph has some undefined points because the original graph has some cosecant. Cosecant is 1 over sine. Sometimes the sine is 0, and so cosecant is not defined. So that's why when we look at our original red graph, we get nothing down here, 0 undefined. And the same thing happens with the numerator. It could be either one. Because one just can be shifted onto the other. So if I look at y equals sine of 2x, well, I need to get the amplitude matched up, so I'll put a 4. And we can see that this has been shifted, so I will just shift this. So once I shift it over pi over 2 units, then the graphs line up again. All cosine graphs are also sine. So here's 4 cosine of 2x. If I just shift this over, shift it by a half of a cycle, it lines up again. I can have y equals negative sine. Oops. That's off a little bit, so I'll shift pi over 2. And everything lines up again. All cosine graphs are also sine graphs. All right. Let us take a look at some other problems. We got 5, 5, problem 4, and 6. So let's take a look at 5.5 problem number 4. The music tone is a fixed pitch frequency that is given a name. If 2 notes are sounded simultaneously, they interfere and produce another tone, often called a beat. The beat frequency is the difference between the 2 frequencies. The beat frequency is the difference between the 2 frequencies. The more rapid the beat, the further apart the 2 frequencies of the tones are. When musicians tune their instruments, they use a tuning fork. Does anybody use a tuning fork anymore? Is anybody here a musician? Do you have a tuning fork? I know it's better for like pianos and stuff, but I don't know. I think the only musicians that have tuning forks are like professional piano tuners. That's all beside the point. They use a tuning fork to sound a tone and then tune the instrument until the beat is eliminated. then the tuning fork and instrument are in tune with each other. Mathematically, a tone is represented by a cosine of 2 pi ft, where a is the amplitude, f is the frequency, and t is the time in seconds. The following table summarizes common tones and frequencies. All right. Write a mathematical description of a tone that results from simultaneously playing D and B. Assume uniform loudness A is equal to 1. So the beat is the difference between the two frequencies. So that's information that we have. Beat is difference between the two frequencies. The beat is the difference between the two frequencies. Write a mathematical description that results from simultaneously playing a D and a B. So the frequency of a B is 494 hertz. And the frequency of D looks like 294 hertz. So our beat frequency is 200 hertz. Equals down here. Let's grab the other questions. The average frequency, did they even talk about average frequency? They never talk about average frequency. Now, they asked for the average frequency. So the average frequency is just half of the sum. So we just add them together and then divide by 2. So 494 and 294. So I take the 200 is the distance between the two. So half of that is 100. So 394. Was that? Yeah, the two frequencies of the frequency of B and the frequency of D, add them and then divide by 2. So the tone is represented with a sine wave or a cosine wave. In this case, a cosine of 2 pi times f times t, where a is the amplitude, f is the frequency, and t is the time in seconds. So we can model the note. We can model the note with sinusoidal function. The amplitude increases the loudness of the note, and the frequency increases the pitch of the note. So a higher frequency will result in a shorter period, and thus a higher note. Oh, that was it. So the key thing in this problem is just that the beat frequency is the difference of the two frequencies. I have a guitar for my own. I could have played a D and a B, and we could have listened for the beat frequency. That's true. I would have brought my guitar down here and they'd be like, well, why did you bring a guitar to class? I thought, I don't know. Are there any questions on the homework? And you'd be like, oh, no. I'm like, oh, never mind then. I guess no reason. So 5.5.6, a very different style of problem. We've got cosine of 5x minus cosine of 13x over sine of 13x minus sine of 5x. So here's where we're going to use our sum to product and our product to sum. I'm forgetting that the answer shows up. So we should be very suspicious about this because we know that some trig identities are going to come into play. And section 5.5 was all about product to sum and sum to product. What we have is a sum of trig identities, cosine and sine. We've got a cosine over a sine, so we can start being suspicious of things like cotangents and tangents. But let's take a look at what this cosine of 5x minus cosine of 13x looks like. Get rid of these. No, because cosine is not being multiplied by these. It's not cosine times 5x and cosine times 13x. It's cosine of 5x and cosine of 13x. So I can't just factor out the cosine because we're not doing multiplication. Multiplication distributes over addition. I keep spelling x wrong. There we go. So once we look at the graph, it looks like a bunch of vertical lines, but we see that around the x-axis, we see it's got this a little bit of bend in it. Oops. We see it's got this little bit of bend in it. So when we look at the graph, it looks like a tangent graph or a cotangent graph. So now that we've got that in mind, okay, go away. Go away menu. There you go. Now that we got that in mind, it says enter the exact fully simplified answer, as if fully simplified means something, but that's beside the point. And we can see that based on looking at the answer that we're going to get something. This is not one of like 8-part problem, is it? No, it's not. So what we need here is a sum to product and the product to sum identity. Here's how I remember our sum to product and product to sum identity. So, oh, suitable for sum to product identities. Yeah, but what if I don't remember it? Oh, it's going to do all this. Okay. So what we end up having to do is I have my resolution so bad. What we have to do is use the sum to product identity because what we have is a sum of cosines and sines, and we can turn that into a product of sines and cosines. So if we take a look at the reason that what's going to make us think of sum to product identities is the fact that we have cosine of 5x and also cosine of 13x. We have trig functions of 2 different arguments. We're trying to combine 2 trig functions with different periods. That's what makes us think of sum to product identities. So the reason we want to think of sum to product identities is that we have a sum or a difference of 2 different periods. We have 2 cosines with different periods. And so that makes us think of sum to product and product to sum identities. And you can see this makes the previous question make a little bit more sense when we're trying to find the average of the frequency, because that's one of the things that's going on here. We're finding the average, the cosine of 5x minus cosine of 13x gets simplified with a -2 sine of the average of the 5x and the 13x. So notice that what we're finding here is that we have so you may notice that I just wrote down what was written down. This is because I can never remember this product, the sum product identity. So this is a big gap in the things that I can remember. I don't know if I'm ever going to be able to remember these. What this does for us is take our two different periods, our two different arguments, and make them into one argument. It gets us to where we end up with one argument. So 13 and 5 is 18 divided by 2 is 9. And then 13 minus 5 is 8 divided by 2 is 4. And then a very convenient thing happens here in that the sine of 4x and then the sine of 4x cancels out in the numerator. Also, the 2's cancel out. So this is what always happens when you're doing trig. You have a lot of trig functions running around. You want to use an identity to combine those things together. In this problem, since when you have different arguments, cosine of 5x and cosine of 13x, that's an indication that you're going to want to use a sum to product identity, which I had to look up. And you can just go look up and then start putting things together. And this one was set up to have a 4x cancel out. Any questions? Comments? What about what? Why? Yeah, sine x plus sine y. So those are the x and the y are the two different arguments that we have. One of the x's would be a 13x, and the other x would be and the y would be the 5x. Those are your two different arguments. Oops, that's not one. So there's your product to sum, and the sum to product is just turning those around, so multiplying by 2 and so forth. All right, so still on our list of things to do, which we will put off until next time, is the review problems 3 and 4. All right, that's gonna do it for today. I will see y'all on Thursday. Everybody have a good couple days, and thanks for playing.